Hello, everyone. A very, very warm afternoon. Welcome to all of you who are joining in and who have already joined to this youth webinar, which the webinars we are passionate about. Each and every webinar is important to us. We try to make the webinar as simple as possible with different topics, different ideas, but those who have joined in, if you have new ideas, new topics, please do let us know. And how would you do that is by registering your kids, going to our website at LetUsTalkIt.com/youth, register your kids there. There are two groups. One younger group from 6 years, and there is an older group from 12 years onwards. And there are prep sessions, and then we have live webinars. And you can also email us at webinar@letustalkit.com to get any information, or you can WhatsApp me. Those who know me, you can do that as well. Having said that, the topic that we have today is the fun facts or amazing facts about physics. And it is said the important thing is not to stop questioning. Curiosity has its own reason for existence. And if it is enough, if one tries merely to comprehend a little of this mystery each day. So with each webinar, we also try to open up a little mystery of something about life, about any particular subject. And if you have any questions, feedback, comments, please do let us know through YouTube and Facebook comment section, or you can join the Zoom link and you can talk to our panelists. Trust me, they are passionate. They come every week and they want to make a difference. So with having said that, we welcome all of you panelists. Great to have you. And over to you, Vivan. I think Virat or Vivan, whoever is the moderator, all are equally involved. Over to you guys. Bye.
Yeah, okay. Thank you, Jilananti. So we're going to be talking about the fun facts about physics. So physics in general is just a branch of, well, um, uh, it's just how the description of how things go around, like gravity. And Isha is going to cover about gravity. Physics is pretty cool. So let's begin with Arjit.
Hello everyone, my name is Ajit Kumar Naru and I am a 8th grader at Camillus Middle School. I like to drum and I'm also a prop maker.
Thank you, Arjit. Now Isha.
Hi, my name is Isha. I am an 8th grader at CMS. I like to draw.
Now Vish.
Hello everyone, my name is Vish and I'm a 7th grader at Portage West Middle School, and I like to read and draw.
Great. And Ajito and Bhavan.
I'm Murat, and I'm learning Blender, which is a 3D modeling software, which I'm going to be using for Unity, which is a 3D game engine.
Great. Now, our table of contents apparently wasn't finished by this time, so I'll just go over a brief. So first we'll have introduced ourselves. That's over. Now we're going to be talking about our topics. Then we'll have our Q&A session. So, Vish.
You went too far.
No, this is your only slide.
My only one?
Yeah.
Did you delete the rest of mine?
Okay, doesn't matter. You can go on.
So, first of all, what is friction? Friction is the force resisting the relative motion of solid surfaces, such as fluid layers and material elements sliding against each other. There are several types of friction. Types of friction. Dry friction is the most common friction. Dry friction occurs when two solid objects touch each other. If they are not moving, it's called static friction. If they are moving, it's called kinetic or sliding friction. Then we have fluid friction. Fluid friction involves fluid or air. The air resistance on an airplane or water resistance on a boat is fluid friction. Rolling friction. Rolling friction occurs when a round surface rolls over a surface, like a ball or a wheel. And finally, we have our facts. Although wheels are great for rolling and reducing friction, they wouldn't work without friction. It would be really hard to stand up without friction. Fluid friction is used a lot in water parks so you can slide smoothly and fast down giant slides. That's all.
Great, Vish. That was all about friction by Vish. I have one thing to add on. Friction is also pretty much every force that keeps things together. Like two components, like the wheel and the axle. If there was no friction, they just slide through each other. And maybe even bolt and nuts wouldn't be possible. So, yeah, I'm going to be talking about Einstein.
Could you exit out of the slide? I think I accidentally deleted someone's slide. I put it back.
Yeah, those were my slides.
Oh, okay.
You did chemical reactions?
Yep.
Oh.
Okay, now it should be settled.
Okay. So for chemical reactions, what are chemical reactions? Chemical reactions is a process that leads to chemical transformation of one set of chemical substances to another. Maybe like matter. Fun facts. Most cars use combustion chemical energy to work. Chemical reactions can cause heat and light, such as a burning log. Many rockets use a combination of oxygen and hydrogen for takeoff, which is a chemical reaction. And that's all.
Okay, thank you about the chemical reactions too. Chemical reactions is also what keeps us alive. Like Vish said, it's usually when two sets of chemicals interact with each other, and this is also what creates salt. Sodium and chlorine are negative and positive charges, and negative and positives attract, so they combine to make salt. So I'm going to be talking about Einstein's works. He mainly talked about relativity, and that's what he was famous for. We all know the equation E equals mc2. Energy equals mass times acceleration squared. And this is true for all objects. So, otherwise, if you don't regard the external forces like friction and stuff like that, it should really work. But external forces really interact with these forces that I'm talking about. I mean, friction interacts with acceleration, and gravity also does acceleration. Mass can be changed by deterioration and addition. So, um, one of my okay. So one of my slides was deleted. Never mind about that. So it was actually supposed to be about general relativity. General relativity is the general relativity theory that Einstein thought of, where all the where all constants are the pretty much the equivalent to that of a normal object, like for instance our sun and the earth. So general relativity tells us that there's a giant mesh called space-time around our universe, and it's what keeps space and time in order because space and time are relative. So he said that when if an object is on the mesh, then it'll cause the mesh to bend, and that mesh is the space and time itself. And since it's bending, anything coming close to that will also get stuck in the bent mesh. But since acceleration and gravity and all those extra forces are really caused by relativity, and he tells us that this is how orbits work. And with this, that's how the Earth rotates around the Sun, and how the Moon rotates around the Earth, and how our whole entire solar system rotates around our galaxy. So, with this, we know that we know that every object has a mass and it bends space-time by a little bit. But this isn't enough for an object to have gravity, like a human. A human is so small that their gravity would be so less that they couldn't even attract an atom in 300 years. It's pretty sad to think about it, but then again, if even small objects had giant gravity, then everything would be scrunched together and turn into a ball of destruction, which we wouldn't like so much. Special relativity happens with objects that are moving faster than the speed of light. And the speed of light is a constant of 299,792,458 meters per second. That is a huge number. So, uh, special relativity says that anything moving faster than the speed of light has special properties. That include their diffraction of light. So if a atom, let's say, was moving at half the speed of light, which is a significant proportion of the speed of light, that's what Einstein was looking for. What would happen if something was fast enough to have a major proportion of the speed of light itself? So when something actually goes this fast, it it itself it doesn't change the speed of light. Like if it's a very jumpy atom and it gives off light, then the light it gives off wouldn't be 1.5 times faster than the normal light speed. But of course, intuition tells us that it might as well be. But no, light is always that constant that I was talking about, 300 million miles, well, meters per second. So, since we can't change the speed of light, things get very weird. And also, he told us how time also changes when you're moving extremely fast. You know how I said that gravity is because of the bending of the mesh of space-time? Well, near a black hole, it's literally a hole through space-time. It's so deep that getting close to it basically slows down time. So, Einstein told us that the closer you get to an object, the more time slows down, because gravity is bending time. And with that, a black hole has enough gravity that if, upon reaching its center, you'd be frozen in time, which shouldn't be possible because of the laws of physics, but Einstein left that for us to figure out. Oh, okay, my slide was placed on the wrong place, but never mind that. So, the bonus is Einstein Rosen bridges. He talked about how there's a literal hole that space-time creates. And that hole must lead somewhere, right? You know how I said at the center of the black hole there must be frozen time. But what if black holes and white holes could be used as portals? I mean, of course, they shouldn't be used interchangeably or called portals. It's still a way to think about them. I mean, if space-time is really a thing and black holes create a massive hole in it, then where does that hole lead to? Another universe with a separate space-time of its own? Well, that's what Einstein told us. And there was also another separate scientist called Rosen who helped with this theory. He stated how black holes could do this, and he gave a few theories and formulas. Together, we know that maybe they are portals, but so far no real proof has been made except these theories. And white holes are actually a great other place for black holes. Since they're the opposite of a black hole, it should be a great place for them to come out of, right? Yeah. So with that, I'm actually done. So now, Virat, you can go on about thermodynamics.
So, adding on to my brother. Oh, never mind. So adding on to my brother, there's also wormholes. That's also Einstein thought of, but that's for later explanation. Anyways, I'm talking about thermodynamics and energy. So here are 6 facts. Fact 1: energy can't be destroyed, and neither can mass. Now, the energy can't be destroyed or created might be a little surprising, but even more surprising is mass. I mean, can you think about it? Have you ever thought of mass not being destroyed in an explosion? Well, you may think that in the explosion, the mass is actually completely destroyed, but no. A lot of the mass gets turned into smoke, some of it turns into ashes, some of it is blown out somewhere else. So, the amount of mass and energy that is put into a system is always exerted out as in another form, or at least out some way, because energy can't be destroyed or created. And because of what Einstein told us as E equals mc2 squared, meaning that depending on how much energy there is, it can also be mass. So energy can also be converted to mass. That's one way that energy can be destroyed. Mass can be turned into energy too. So with this means that energy is not destroyed, mass is not destroyed, just converted into a different form or the other. Now, next fact. Now, every action has an equal and opposite reaction. Now, a lot of us know it, but can you think of any examples? I mean, if you push a door, it doesn't come back straight to you. So, what is the reaction? Well, the equal and opposite reaction is friction. On the hinge doors, they move around. They give friction. Like Wish said, there are different types of friction. So this friction is a loss of energy, and it gives an opposite reaction toward this push of the door. There's also aerodynamics. The door is not like a plane, so it's very less aerodynamic. It has a lot of air pressure, so the air will push back on the door. So, next fact, entropy never decreases. Now, you may be thinking, what even is entropy? Well, entropy is the orderliness of a system. Now, it means that if you left out a coffee drink to cool and you left out in the environment, slowly over time, everything becomes more and more balanced. And that's when entropy is at max, when the coffee drink and the environment are at the same temperature. Now you're at equilibrium. So that's when entropy at max. Now the entropy is never at max in the universe because it's constantly increasing in our universe. And things are getting slower, things are getting less temperature, so over time, slowly and slowly, we're gonna reach max entropy and nothing's gonna move.
Virat,
Yes?
So what about heating stuff? Like heating stuff increases its temperature and makes them less dense, right?
That's true, but it there is just like that. Every action has an equal and opposite reaction. I mean, the air is also slowing it down, meaning that the air is being pushed around. The air is being quietly heated. It's taking on things, and it's also being cooled. So entropy is staying same here. It's not increasing or decreasing.
Okay, thank you.
So, fact 4, energy only converts into different forms. I already explained that. Fact 5, energy can create virtual physical mass. That's also true. One thing to be talked about is like in the particle accelerators, two atoms colliding wouldn't do much, but because of they're being accelerated to near the speed of light, they have a lot of virtual mass. And fact 6, the amount of mass is from a process is always the same. Like I said, and in an explosion, only mass gets converted into a different form. It doesn't get destroyed. Next slide. Okay, so energy. What about energy? Well, there are different types of energy, like chemical energy that we talked about, nuclear energy that are just going to be talking about, wind energy, but most of these actually come from one single source. Now, these are all different types of energy, and as they go to our computers release it off as heat energy. Now, this heat energy goes into the air, and the air releases that kinetic energy.
Is energy a dwarf planet?
Now, yeah, sorry for that. I left that one blank. Anyways, yeah, that was pretty much all.
Okay, thank you, Barat. Energy is quite interesting, and it's the thing that keeps everything in motion. I said that chemical reactions are what keeps us alive because we're made of chemicals. And that's right, Wish, but energy is a byproduct of this, and that's why we have enough energy to talk, breathe, and move.
That's why we're also hot. We release our energy as heat too.
Yes. Okay. AJ?
Thank you, Vivan. Starting off with nuclear physics. Nuclear physics is a field of physics that studies atomic nuclei and their constituents and in interactions in addition to the study of other forms of nuclear matter. Nuclear physics should not be confused with atomic physics, which studies the atom as a whole, including its electrons. So nuclear physics, we're starting off with its history. The history of nuclear physics, as a disciple, distinct from atomic physics, starts with the discovery of radioactivity by Henri Becquerel. Um, Before I keep going, I don't know how to pronounce all the names in this slide and other slides that continue. I'm sorry if it offends anybody, it's just I don't know how to pronounce them properly. As I was saying, made while investigating phosphorus in uranium salt. The discovery of the electron by J.J. Thomas a year later was an indication that the atom, the internal structure. Vivan, could you go to the next slide, please? I'm sorry, I didn't say that before. Discovery of the electron by J.J. Thomas a year later was an indication that the atom had internal structure. At the beginning of the 20th century, the accepted model of the atom was J.J. Thomson's plum pudding model, in which the atom was a positively charged ball with smaller negatively charged electrons embedded inside. In the years that followed, radioactivity was extremely investigated, greatly by Marie Curie, Pierre Curie, and others. By the turn of the century, physicists has also discovered the types of radiation inhabiting the atom, which they named alpha, beta, and gamma radiation. Experiments by Otto Hahn in 1911 and James Chadwick in 1914 discovered that the beta decay spectrum was continuous rather than the discrete. Electrons were injected from the atom with a continuous range of energies, rather than the discrete amounts of energy that were observed in gamma alpha decays. This was a problem for nuclear physics at the time because it seemed to indicate the energy was not conserved in these decays. The 1903 Nobel Prize in Physics was awarded jointly to Becquerel for his discovery and to Marie Curie for their subsequent research into radioactivity. Rutherford was awarded the Nobel Prize in Chemistry in 1908 for his investigations into the disintegration of the elements and the chemistry of radioactive substances. 1905, Albert Einstein formulated the idea of mass equal energy equivalence, equal to mc squared. While the work of radioactivity by Becquerel and Marie Curie predates this, an example of the source of the energy of radioactivity would have to wait for the discovery that the molecules itself have composed of smaller continuates, the nucleus. Could you go to the next slide, please? Modern nuclear physics. Talking about modern nuclear physics, there's nothing much that was added into the modern nuclear physics because most of it was covered in the past. There were slight indications slight additions to it, but that's all there is. There's nothing much about it. Discoveries in nuclear physics have led to the applications in many fields. This includes nuclear power, nuclear weapons, nuclear medicine, and magnetic resonance imaging. Industrial and agriculture is isotopes, ion implantation in material engineering, and radiocarbon dating in geology and archaeology. Such applications are studied in the field of nuclear engineering. Particular physics evolved from the nuclear physics, and two fields were typically taught in close association. Nuclear astrophysics, were the application of nuclear physics and astrophysics is crucial in explaining the inner working of the stars and the origin of chemical elements. In the next slide, I'll be talking about uses of nuclear physics. The uses of nuclear physics there are many, as I said in the slide before, but there are three main forms of nuclear physics. First, we have nuclear energy, which uses radioactive materials as a variety of imported uses in electricity generation. Medicine nuclear physics is a subfield in medical physics that pertains to the therapeutic and diagnostic applications of radiocluides, except those used to sealed sources of therapeutic purposes. The equipment associated with their production use material user measurement and evaluation. Agriculture. Nuclear technology uses radiation to improve the productivity of the entire food chain in substantial manner. Neutron matters improve the irrigation practices and that help conserve the water and protect vulnerable land. Tagging fertilizers and the radio stoppers can determine how plants are using nutrients. These are all the uses, the history, and the thoughts about modern physics in nuclear physics. Thank you.
Great job, AJ. I especially liked how you explained the uses of nuclear physics. And also, nuclear energy is mainly produced in two forms, fission and fusion. Fusion is when two atoms are fused to give off massive amounts of energy, and fission is where two atoms are collided and their byproducts which release energy. That's also um, nuclear energy can be based on fission or fusion. Nuclear bombs are mainly made up of fission. Thank you, Virat. And also, medicine, they're usually used to treat cancer.
Yeah, it is used for cancer, but the rates there are used for cancer, but the use of using it in cancer is very risky. So I just didn't want to add that because I don't think it's a good idea to use nuclear physics in treating cancer because it's very risky and it harms the person in many ways.
Yeah, there are usually side effects, but the main side effect is that they lose all hair. Hair is really vulnerable to radiation.
Yeah.
Okay, now Gravity by Isha.
I'm going to be talking about gravity. Next page. These are just some facts about gravity. When the object falls, the gravitation pull is 9.3 ml plus. When the falling object is only affected by gravity, it is called to be said to be free fall. Mass is a measure of the amount of matter an object contains. Next page. To be nearly weightless, you would have to be far from the Earth. Astronauts experience this feeling when they are in space.
Okay, great, Isha. Gravity is the thing that keeps us on Earth. Otherwise, we'd be floating away. And also, the air. The air around us, the atmosphere, is only retained by Earth's gravity, not any other external forces. And that's also why we can breathe. So now, it's our Q&A interaction session. Do you have any questions? Well, you can join into the Zoom call if you do. Okay. I'm going to stop sharing. Okay. Dave, now you can ask any questions.
No, I don't have any questions.
Oh, okay.
I see Dave has joined. Dave, can you hear?
Yeah, I can hear.
Okay, so do you like physics? I know it's the first time.
Dave is actually our friend.
Yeah, I know. So I was just, I mean, asking whether he has, what's your passion? What are your hobbies? Dave?
My hobbies are it's usually it's playing Roblox and playing with my friends outside.
Okay,
And going to car showrooms.
Yeah,
going to car shows?
car showrooms.
Oh, okay, that's nice. So you have a passion for cars, right?
Yeah.
So what car you like best?
Well, I forgot the name, but it's like a supercar and pretty expensive.
Okay.
Uh,
Okay. Yeah.
So, Wish said how combustion energy is how cars run off of. I'm really excited to see if there are radioactive powered cars because Curiosity actually runs off of radioactive energy sources.
It's called an RTG. It uses
Yeah.
radioactive isotopes to produce energy. So it's great to see how we used the Einstein's E equals mc2 theory a lot of times. I came up about it when I was talking about Einstein, and Virat talked about it when he talked about energy and mass conversion, and AJ talked about it for particle colliders. The Einstein theory was very useful because it provided all these uses. He mainly talked about how like mass can be converted into energy, and this came up with many other applications, like using uranium atoms and well colliding them to get energy. And this is how nuclear physics works.
With this amount of energy, you could make a lot of other objects. We already have 3D printing. Maybe we could make a, a, a space on moon. It's actually possible to use nuclear energy on the moon. So with that, you could probably make some 3D printed materials with energy, but it'll be inefficient though.
And also Hyperloop. Loop turns out. It basically vacuums all the air out of its tubes, making it basically no air friction. Like Wish said, air friction is what keeps planes from going any faster. So basically, Einstein's theory got to be used again. So even though a plane isn't that big, well, it is a few tons, but to our scales, the sun is like quadruples, like wait no, lots and lots of times bigger. And despite this, they're weighed down by the air a lot. Since they're going really fast, their energy is high, and air friction acts on them the faster they're going.
So if we have a little bit of time, can we discuss about like what's one of the most powerful type of physics or energy source?
Okay.
I'm thinking maybe friction, because friction keeps all of the things together, and it's also like one of the main energy sources, like turbines.
Yeah. And without it, nuclear physics wouldn't work because for something to collide, it needs to have some friction, or else they'll just slide past each other like some sort of ice on ice, or butter on ice, or butter on butter. AJ, did you say something? You were muted. Okay. So I think that's it.
So all questions answered?
Well, we didn't really have any questions. We just talked a little bit.
Right. Any other fun facts anybody knows or it came to your mind?
Dave raised his hand. Yeah, you can go ahead.
I finally remembered the name of my favorite. Well, it's like a 5,000 horsepower car. Well, it's called the Devil 16. Well, it's not. The 16 is not really written in numbers still. Instead of the I for the fourth letter, it's instead of I, it's E.
Do you really like it because part of it is your name?
No, because
that was a good catch.
it's actually really fast though.
Cool.
What is?
So great job, everybody. It was fun talking about physics, considering that it's one of my favorite fields, other than medicine, of course.
Yes. So yeah, great job as always. And yeah, we have a new attendee today and our future panelists. Hopefully we'll see you, Dave, for our prep session, which happens every Tuesday and Thursday from 4:30 p.m. EST. And we go live every alternate Saturdays at 4 p.m. And yeah, we have for the younger session, again, prep session every Tuesday and Thursday, 8:30 p.m. EST. And we go live every alternate Fridays at 8:30 p.m. EST. And if anybody wants to join for public speaking, for interaction, for having a good time, having some virtual friends, you can register at LetUsTalkIt.com/youth. So with that, we end today's session. Thank you everyone for joining in and hope you have a wonderful weekend ahead. Bye.
Bye.
Bye. Thank you.
Bye.
Okay, all the panelists can stay on the meeting. We're going to discuss the next topic. Okay, next topic time.